Single-phase AC induction motors are everywhere. These motors power our household appliances. They are in fans, refrigerators and washing machines. They are reliable, simple and efficient. But how do they work? Let's dive in. These motors run on single-phase AC power. This is the type of electricity we have in our homes. The magic happens when electrical energy converts into mechanical energy. This makes the motor spin. Every single-phase AC induction motor has two main parts, a stator and a rotor. These two components work together to convert electrical energy into mechanical energy, which is essential for the motor's operation. The stator is the stationary part. It remains fixed and does not move, providing a stable magnetic field for the rotor to interact with. It's like the outer shell of the motor. The stator is crucial because it houses the coils that generate the magnetic field necessary for motor operation. The rotor, on the other hand, is the part that rotates. It is the moving component that turns to produce mechanical work. It's located inside the stator. The rotor spins within the magnetic field created by the stator, which induces a current in the rotor bars. The rotor is typically made of aluminum or copper bars. These materials are chosen for their excellent electrical conductivity and durability. These bars are arranged in a cylindrical shape. This cylindrical arrangement allows the rotor to rotate smoothly within the stator. The stator is made up of coils of wire. These coils are essential for creating the magnetic field that drives the rotor. These coils are wrapped around iron cores. The iron cores enhance the magnetic field generated by the coils, making the motor more efficient and powerful. When we apply single-phase AC power to the stator windings, something interesting happens. The alternating current creates a changing magnetic field around the stator coils. This changing magnetic field is called magnetic flux. The magnetic flux expands and collapses as the AC current alternates. This continuous change in the magnetic field is important for inducing current in the rotor. Section 4. Induced current in the rotor and creation of a new flux. The rotor, sitting inside the stator, experiences the changing magnetic flux. This flux induces an electric current in the rotor bars. Remember, the rotor bars are conductors. This induced current creates its own magnetic field around the rotor. Now we have two magnetic fields, one from the stator and one from the rotor. These fields interact with each other. Section 5. The problem of initial motor movement. In this section, we will delve into the intricacies of why an AC motor doesn't start rotating on its own. Here's the thing. The interaction between the stator's and rotor's magnetic fields doesn't automatically start the rotation. This is a fundamental issue that needs to be addressed for the motor to function properly. Why? Because the magnetic fields are initially aligned. When the fields are aligned, they don't create the necessary torque to initiate movement. They are pulling in opposite directions, resulting in a standstill. This alignment causes a deadlock situation where no rotational force is generated. This is like having two equally strong people pulling a rope from opposite ends. The rope won't move. The forces cancel each other out, leading to no motion. To solve this, we need a little help to give the rotor a push. This initial push can come from various methods, such as using a capacitor or an auxiliary winding, to create an initial phase difference and start the rotation. Section 6. The capacitor, the unsung hero of the motor. Here's where the capacitor comes in. Often overlooked, this small but mighty component plays a crucial role in the operation of electric motors. This clever component is connected to a separate set of stator windings called the starting winding. These windings are essential for giving the motor the initial push it needs to start turning. The capacitor shifts the timing of the current flowing through the starting winding. This timing shift is critical because it helps to create the necessary conditions for the motor to start. This shift in current timing creates a phase difference between the main and starting winding magnetic fields. The phase difference is what sets the stage for the motor's operation. This phase difference generates a rotating magnetic field within the motor. The rotating magnetic field is the key to the motor's ability to start and run efficiently. This rotating field finally gives the rotor the push it needs to start spinning. Without this initial push, the rotor would remain stationary and the motor would not function. The rotor then continues to chase this rotating field, trying to align itself with it. This continuous alignment process is what keeps the motor in motion. This continuous chase is what keeps the motor running. The capacitor, though small, ensures that the motor starts smoothly and runs efficiently, making it an unsung hero in the world of electric motors.